Hey guys, so far you've learned that you put a bunch of animals of the same species together, you form a population. When we put a bunch of different populations together, we form a community. Wonder what happens when we put a bunch of communities together? Well, we form an ecosystem. So we're going to go ahead and jump right into ecosystem dynamics. Here we go. So this picture is just to help you put into, like a picture format, what I said in the introductory slide. We start off always in the biosphere, we're going to start off as a single organism. When you have a bunch of those same kinds of organisms, we then make a population. From a population, we have a bunch of different populations coming together. We have a community. You punch a bunch of different communities together, you get an ecosystem. Eventually, we're talking about the entire living section of our world, also known as the biosphere. So when we start thinking on the large scale of an ecosystem, there's some questions that have to be addressed. Things that we probably haven't already thought of when we talked about communities or populations. Things like, what's going to limit the productivity level of this ecosystem? How are nutrients going to move around and in and through the ecosystem? And how is energy going to move through the ecosystem? Because literally you're going to have bunches of organisms that are all interrelated, all interdependent, all interacting with each other, and all of whom will need nutrients and energy and shelter and all of those resources that we've talked about before. So ecosystems are all about cycling matter and the flow of energy. It's all about moving these things around so that everyone can get a little bit of what they need. So this is where biology and physics really do have a big tie-in. We go back to those laws of thermodynamics. Like I told you before, there will be a place where we address exactly what those are and what those mean for a biological system. So for right now, if you're looking at this picture, all I want you to pay attention to are the processes taking place. We have things or processes like photosynthesis. We have digestion and growth. We have excretion and death. And of course we have respiration. Notice who's doing what and who's relying on who so that those processes can take place. So let's get into these thermodynamic laws. The first law of thermodynamics says that energy cannot be created or destroyed. It can only be transformed from one form to another. So we never truly make new energy. We're just changing the form of the energy that we were using. So if you look at this picture, we have a guy who's mowing his lawn or cutting his grass or whatever, and he's using a lawnmower to do that. So let's think of some of the kinds of energy that we could be seeing. We'll definitely have the chemical energy of the gas being converted into the mechanical energy of the parts of the lawnmower that will be doing the job, like the pistons and the blades and all of that. We have chemical energy from the food that this man ate being converted into mechanical energy, which allows him to push the motor and to walk with the mower, sorry. So allows him to push the mower and walk with the mower so that he can cut his grass. We have radiant energy, which is coming from the sun. I don't have a picture of the sun here, but obviously you cut grass outside and not inside, so there should hopefully be sunshine. But we have radiant energy from the sun that's going to be converted into chemical energy, which we're going to use in the form of photosynthesis, which helps that grass to grow, so that's why he has to cut it every single time. So we're not really remaking energy, we're just taking what's already available to us and changing its form so that we can make it more usable. The second law of thermodynamics states that as energy conversions occur, some of the usable energy is converted into an unusable form, also known as heat energy. So it's not that it's lost, it's just not usable. Well, when you increase heat energy, you're increasing entropy, you're increasing disorder. So even though we could use that heat energy to do work, it can only be used if there is what we call a heat gradient. So this is where you have to think of how much energy am I putting in and how much actual energy am I getting out of it, plus how much heat am I getting out of it. So if you think of a car, you're putting in energy, chemical energy in the form of gasoline, but as you drive that car, it's going to be transformed from chemical energy into mechanical energy, so the car will actually work. But think of driving your car for a long period of time and you get out and you put your hand on the bonnet. You normally the bonnet normally feels hot, or sometimes you can feel the heat radiating off of the car. And this happens even when it's, it's like winter time. It happens constantly. Well, that heat is unusable heat energy. So even though you got some mechanical energy out of the movement of the car, which we got from the gasoline, we also created a lot of unusable heat energy. Okay, now the more heat energy you're creating, the more entropy or disorder you're also creating. So the entropy of the universe is constantly increasing. Every single time we do something that produces heat, we increase entropy. And that's literally from driving a car to running around outside to, whatever you do that produces heat. So those are the two laws of thermodynamics, and they play a big role in ecology. Another thing we have to consider when we start talking about thermodynamics is free energy. So your free energy is the energy that's available to do work. If you're working in a closed system, one that isn't constantly being resupplied with energy, your total amount of energy is going to be your free energy or your usable energy plus your unusable energy. So we can write that out. Total energy is going to be free energy plus unusable energy. Okay, so like I said, the free energy is the energy that's available to do work. It's already there and it's already in a usable form. But if you look at this diagram, this showcases this really well. If you realize every time you undergo an energy transformation, every time that energy changes form, so from radiant to chemical, from chemical to mechanical, whatever that change is, you're going to lose some of your total amount of usable energy. The more transformations that happen, the less usable energy you have, and the more unusable energy you have, or you start gaining, because most of these processes will at some point produce heat. So every time we have heat, we're increasing our unusable energy. Okay, now another thing to keep in mind is the amount of free energy in a system is always lower than the total energy of the system unless the system is an open system. So in a closed system, we may start off with 100% usable energy, but over time, we're going to have less and less usable energy. In an open system, and the Earth is an open system because we're constantly getting energy from the sun, the amount of free energy is, let's say, replenished, for lack of a better term, every time that there is, sunshine and sunlight coming through to our Earth. All right, so I said that we're talking about ecosystem dynamics today, so let's start off by talking about what an ecosystem is. So an ecosystem will be all the organisms in a community plus the abiotic factors that those organisms have to deal with. So ecosystems are really just giant transformers of energy and processors of matter. We just changed the form of tons of things, energy and matter. Ecosystems tend to be self-sustaining, but they do have some needs. They're going to have to be able to capture energy in some form. That energy has to be able to be transferred from one thing to another, and nutrients must be able to be cycled through all parts of the ecosystem. Once these three things are being met, that ecosystem becomes self-sustaining. So how does it happen? Well, it all starts off with the energy from the sun. That energy is going to flow through that ecosystem, that location, and it's going to start the whole process of energy transfer. Once we have energy, we can start making nutrients, so then nutrients are made and cycled through the system, and we have a self-sustaining ecosystem. Keep in mind that nutrients can only be cycled. They have to be created from something, and they always need an energy input in order to do that. Our inputs into an ecosystem will always be energy and nutrients. Now, what about the organisms that don't get energy from the sun? How are they getting their food? How are they getting their nutrients? Well, something else is going to utilize that energy and turn it into a usable form of matter for those organisms that can't make it themselves. So how are things made in an ecosystem? Things are made through primary production. And I just realized I didn't give you an actual definition. So I'm going to try to write it out. Hopefully you can listen to what I'm saying and take it down. Primary production is the making of organic compounds from either atmospheric or aquatic carbon dioxide. I'm going to write that down. It's the making of organic compounds from atmospheric, and I'm just going to put ATM for atmospheric, or aquatic CO2. So we're going to take just carbon dioxide, either from the atmosphere or from the water, and we're going to use that to produce or to synthesize organic compounds, organic molecules, biomolecules, macromolecules. They have tons of different names, and you'll get used to them very quickly. So primary production can happen through two processes, either photosynthesis, which is going to utilize solar energy, or chemosynthesis, which is going to utilize hydrothermal energy. So of course the solar energy is coming straight from the sun. It's regular photosynthesis. Lots of organisms are capable of doing photosynthesis, which is using the light to transform it into an actual organic molecule. We're using the energy, from the light to transform carbon dioxide into a usable organic molecule. Whereas chemosynthesis is using either the oxidation or reduction of chemical compounds, normally sulfur-related compounds, as a source of energy. So we're going to find that this happens with a lot of our terrestrial animals. We do have bacteria and some other things that can do photosynthesis, and we'll find that this process tends to happen where we have a large amount of chemical compounds that are readily accessible, so like hydrothermal vents and stuff like that, volcanoes, things like that. The organisms that are responsible for primary production are known as primary producers. The other term we can use to describe these organisms would be the word or term autotroph, which you are probably familiar with. If I could get my pen to work, that'd be great. Okay, so these are going to be the organisms that really make the first set of organic compounds, and they start off the cycling of nutrients in an ecosystem. So we can take the concept of primary production or primary productivity and split it into two sections: your gross primary productivity and your net primary productivity. If any of you have a job, you can think of this as your net pay versus your gross pay. It's kind of the same concept. So gross primary productivity is going to be the total amount of energy that the producers are able to convert into chemical energy. Just every single thing they can possibly convert. So that, like your gross paycheck, that would be all of the money that you actually made before they took out anything for taxes or health insurance or anything like that. But you have to remember that these producers are actual living organisms, which means that they do have some energy requirements of their own. They're going to need some energy in order to support themselves through things like cellular respiration and growth and, the moving of parts and pieces and the opening and closing of different structures. So once that organism has utilized some of the energy to do its day-to-day activities, we have our net primary productivity, which is all the energy left after the organism has taken care of its own needs. So think of it as your net paycheck. After they take out all of those deductions, it's the money you're actually bringing home. Your net primary productivity is the chemical energy that's left available to be used by a different organism. Okay, so hopefully that makes sense. So here's another visual to help with the picturing of nutrient cycling, you should see some terms that are familiar to you, like consumers and producers and decomposers. And it's just essential that you realize that when we talk about nutrient cycling, we mean that they're going to everything in that ecosystem that's alive. But nutrients can also be held by parts of our ecosystem that are abiotic, they're non-living. So we can store nutrients in some of these abiotic features, like the soil, for example. So unlike nutrients which cycle through our ecosystem, energy actually flows through the ecosystem. It all comes from the sun. It all starts off as radiant energy. And then producers, and it says plants here, but just realize that we mean any kind of autotroph. All right, so we made that little change. Make sure you amend that in your notes. So that radiant energy is going to be utilized by autotrophs or producers to make actual nutrients. Some of it will be converted into an unusable form of energy called heat. It's not really a loss of energy. We're losing the usability of the energy. Okay, so then some of that energy is going to be utilized by primary consumers or herbivores. Once they eat once they eat plants, they're going to get energy from their food. And then if carnivores eat herbivores, they're going to get energy from the herbivores. So energy is just flowing through the system, and we're also at every level losing some of our usable energy. I'm also going to make that correction really quick. All right, so we're losing usable energy. Just make that amendment. Now, since attaining food is a very important part of an ecosystem, it leads us to talk about food chains and food webs. And I'm not going to spend a ton of time on this because this is something that you guys tend to have a very good handle on. So we're just going to go through it really quickly. So you can take our food chain or our ecosystem, and we can divide it up into what we call trophic levels. So trophic levels show the feeding relationships between a couple of different organisms, or sometimes just two organisms. It always starts with energy from the sun, or from chemosynthesis. We're getting that energy from some kind of chemical compound, but the energy is being input from someplace. That energy is going to be captured by producers, which is going to be one of the lowest levels of your food chain, and it's actually the very first or starting level of all food chains. It sometimes gets confusing because we tend to showcase the decomposers. Like if you look at this picture, we tend to showcase the decomposers as being under the autotrophs, and it's normally because they're found in soils, but realize that your producers are your first level of your trophic level or your food chain. The food chain only goes up 4 or 5 levels because once you get above that, we start having an inefficiency of energy transfer. What that really means is that the amount of energy available from one organism to another is just so little, it really can't sustain whoever is on the very top of that food chain if we go up too high. So that's why it tends to be only about 4 to 5 levels long. All of these levels are connected to decomposers because the decomposers are really the last guys to do any kind of work or get nutrients. And it happens because as everything else dies, so as our producers die, our consumers die, our carnivores die, they're all going to be decomposed and recycled by our decomposers in the form of bacteria and different kinds of fungi. So, as I mentioned before, there is an inefficiency of energy transfer, and it goes back to that net primary productivity that we were talking about. There is going to be a loss of energy between the levels of the food chain. And remember, it's usable energy. A lot of the energy as we go from one level to the next is being converted into heat, which isn't usable, at least not the way we need to use it. Okay, so where is that energy lost? It's the cost of living. We have to use it to grow. We have to use it for cellular respiration. We have to use it for waste materials. It's just daily life costs energy. You can't do stuff unless you have energy to support your actions. So what it boils down to is that the loss of energy between the levels of the food chain means that you can only feed fewer animals in each level. And if you think about it, the first level is always our producers, and we tend to have a lot more producers than we have anything else. If you think of how much grass and how many trees and just how many things can do photosynthesis, there are a lot more of them in the world than the amount of cows we have in the world, for example. And it's because you need to eat more of everything underneath you to get enough energy to live. So from this information, we can plot what we call an energy pyramid, and that's what this picture shows. It also shows us transformation, or what we also call the 10% rule, and that's the amount of energy that's passed on from one level to the next. We lose about 10% of that in the form of unusable energy, heat. All right, so let's refresh our memories about those thermodynamic laws, because right now we're going to talk about energy, the 10% rule, and how the laws of thermodynamics have something to do with all of that. Remember, our first law says we can't make or destroy energy, we can only change its form. The second law says that every time energy transformation happens, some of the energy is converted to heat, which is unusable, and while that heat increases entropy, it doesn't increase the amount of energy available. The energy itself isn't lost. Instead, it's such a low quality, we can't actually use it. So what this diagram is showing is that at every transformation, heat is moving out of this system. This whole diagram represents a system. This is can never say that together. This is in agreement with the first law of thermodynamics, which again says you can't make energy, you can't destroy energy, you can just change its form. So some of the energy is being transformed by the organisms to use for their life processes, whereas some is available when they're consumed at the next level, and some of it is given off as heat. So we're just changing the form of all of the original energy that we get from the sun. So where do we come to stand in this food chain or in this food system? Well, the dynamics of energy through ecosystems have a lot of implications for human populations. It boils down to how much energy does it take to feed a human. If we are vegetarian, we are primary consumers. So we just eat we eat primary producers, corn, tomatoes, whatever, and that's how we get our energy. But if we are meat eaters, we become secondary consumers. So we go up one more level. We're still going to get some of that nutrients from our producers. We're also going to get nutrients from primary consumers because we're on top of them. So a food chain is what we would see if we just looked at one small part of the ecosystem. But when we start looking at communities and ecosystems as a whole, as a big idea, we branch off into food webs. And food webs are just food chains that are all linked together. Okay, so they can all be broken down into individual chains, but when we look at them holistically like this, we call it a web. It's a game of who eats whom. And you have to realize with food webs that one organism or one species may play several different roles. They can be a primary consumer or a secondary consumer or a producer. They play different things. So if you look at examples of organisms that eat both meat and eat plants, they're going to be on multiple levels. So while we tend to focus on nutrients and energy, there are a couple of other things that cycle through an ecosystem, and they're very important. The ecosystem wouldn't be able to survive without these various minerals. So we're going to start talking about some of these. The first one is going to be nitrogen. So nitrogen is cycled through what we call the nitrogen cycle, and it is very important for the proper development of both plants and animals. And the way that it's moved around is very, very unique. But one of the things that we have to pay particular attention to, and I'm going to circle these, are the role of these different kinds of bacteria that you will find throughout, my pen got stuck, throughout this system. If these bacteria did not exist and were not able to do their job, this cycle wouldn't work. And if this cycle didn't work, then lots of plants and animals would not have what they need. I missed one in there. Okay, so in the nitrogen cycle, nitrogen's found atmospherically, but it's not in a usable form. And since it is a very big requirement for living things, it means that we have to find a way to take nitrogen out of the atmosphere and put it into our bodies so that it can be utilized. So there are a couple of ways that you can do that. There are some kinds of bacteria that can naturally utilize nitrogen in the atmosphere and turn it into a usable form. So examples of those would be nitrogen fixing bacteria, and these tend to be found in the roots of our peas and bean type plants, also known as legumes. And that's what they do. They take nitrogen out of the atmosphere and they make it into a usable form for that plant to use. We also have nitrogen fixing soil bacteria. It's the same kind of bacteria. They do the exact same thing, but these guys are found in the soil versus these guys are found in an actual plant. What they do is they turn nitrogen into a usable form known as ammonia. Then we can cycle this usable nitrogen once the plants have it and then animals eat those plants. They will now attain the nitrogen needed. But when the plants and the animals both die, the bacteria and fungi that make up our decomposers are going to break their bodies down and return the nitrogen to the soil, again, still in a usable form of ammonia. When it's time to return that nitrogen back into the atmosphere, because remember this is a cycle, we have different kinds of bacteria for those purposes. We have what we call nitrifying bacteria and denitrifying bacteria. So what nitrifying bacteria do is they take this ammonia and they turn it into nitrates and nitrites. Hopefully you remember that from chemistry. This is a form of nitrogen that regular plants can just absorb through their leaves. So if they're not plants that have this association with these bacteria, they can just absorb this kind of nitrogen straight from the ground. Denitrifying bacteria will take these nitrates and turn it back into atmospheric nitrogen. So this is how that cycle works. Again, I need you to understand that if we were to remove all those different kinds of bacteria, this entire cycle would fail. And then life as we know it wouldn't be able to exist because we do desperately need nitrogen for a lot of different things. Now, while the phosphorus cycle isn't as important in terms of your knowledge for AP biology, one of the things I do want to point out to you is one of the differences, and this is kind of why it's not as important. This is what we call a non-global cycle. The nitrogen cycle that we just looked at, that would be a global cycle. But the phosphorus cycle is not global. And it's because phosphorus is not or does not exist in a gaseous phase. So you never have phosphorus like in the atmosphere, for example. It's only in a liquid state or a solid state, which means it never enters the atmosphere. This cycle just happens in the ground and through our water system. This one you can look at, it's pretty much the same thing. Okay, water cycle I'm not going to go over because this has been hammered into your head forever, but do know that it is a global cycle because water is capable of existing in a gaseous phase. Now, whereas the amount of water on Earth stays fairly constant, you have to remember that it's distributed in 3 different ways, solid, liquid, and gas, so that might alter. Also know that this is one of those cycles that climate changes greatly affect the distribution of. Okay, carbon cycle. Highly important, very valuable cycle. Is it global? Yes, it is, because CO2 is capable of existing in a gaseous state. Why is this so important? Because all of our building blocks, all of our organic molecules are synthesized from carbon dioxide. Carbon is vitally important to living systems and bodies. So without the carbon cycle, we wouldn't have the parts and pieces needed to build our actual bodies. We would not exist. We cannot forget about the carbon cycle. And again, it's one of those things where you're trying to get carbon out of the atmosphere. Now, in the atmosphere, carbon exists as carbon dioxide. So you got to pull it out of the atmosphere. We do that through photosynthesis for the most part. Notice, photosynthesis is really the only process that takes carbon dioxide out of the atmosphere. And then it's sent to primary consumers. We can send it down into the soil. It goes back into the atmosphere through 2 main processes. cellular respiration. Once you're living, you are going to respire. So that's how most of the carbon dioxide gets back into the atmosphere, or through the burning of wood and fossil fuels. All right, so hopefully this wasn't too painful and it was mostly clear. Make sure that you write down or you star or highlight anything that you have questions over, and I will try to devote a little bit of class time to going over and answering those for you. See you soon.